morning and welcome to this next lecture on sound and structural vibration. We started looking at this new topic of a plate set in a rigid baffle and radiating sound. We had reached up till this point. So the intensity we had computed is given by this expression, okay, where this expression indicates that you choose the cosine when P is odd or Q is odd. Okay, P comes in here, Q comes in here, and you choose the sine when P is even or Q is even. Okay, so that's the intensity. Now this is the far field intensity. Okay, we had done a far field approximation on the Rayleigh integral. So this is far field intensity. Now we ask the question, where is the intensity maximum, or under what conditions is it a maximum? We ask this. Okay, and just on the surface of it, looking at the expression, it seems like when the denominator goes to 0. Okay, it seems like when alpha is equal to P pi and beta is equal to Q pi. Okay, but remember, suppose we choose the 1-1 mode P comma Q is equal to 1 comma 1, 1 comma 1. Okay, then P is odd and Q is odd, then both places I should choose the cosine. Okay, I should choose the cosine here and cosine here, and alpha is now equal to pi and beta equal to pi. Then we will have cos alpha by 2, which is pi by 2, and we will have cos beta by 2. Okay, both are equal to 0. So at alpha equal to P pi, denominator is 0 and numerator is 0. So we have a 0 by 0 form, 0 by 0 form. So we have to use L'Hopital's rule. Okay, so it is doable. It's a little cumbersome but doable. So I will not do it here. Just a simple calculus will get you the expression. So let me just write the expression for maximum in I. Okay, maximum intensity. That expression looks like rho 0 c magnitude b tilde pq square by 2 k a b by 8 pi r whole square. That is the maximum value. Okay. Now this is time averaged value, and therefore there is no time in it. There is only space, which means distance and angles. So and frequency. So at what frequency at what frequency does Imax occur? At what frequency does it occur? Okay. So let us see, alpha is equal to p pi, which implies Ka sin theta cos phi is equal to p pi. Okay. Now, okay, then beta is equal to q pi, which implies Kb sin theta sin phi is equal to q pi. Both these are happening. Okay. Both conditions are happening. Both conditions are happening. Okay. So now, what does it mean? Sin theta cos phi is usually less than 1, okay, for most angles. Then sin theta sin phi is also less than 1 for most cases. Okay. So that means what? It means that Ka multiplied by something that is less than 1 is equal to p pi, which means Ka is greater than p pi. Similarly, Kb into something that is usually less than 1 is equal to q pi, which means Kb is greater than q pi. Okay. So we are insisting on both conditions being satisfied. That is important, because somebody could say that no, sin theta cos phi can be 1 at some place. Yeah, it can be 1 at some place, but at that place sin theta sin phi will be 0. Okay. Somebody could say that this statement is not true. Yeah, that is correct. It is equal to 1 in some places, but when this is equal to 1, this is equal to 0. So we are insisting on both conditions being satisfied. Okay. So those will happen for some odd angles, not peak values like 0 or pi by 2, etc. Okay. So essentially now what that means is Ka must be greater than p pi and Kb must be greater than q pi. Now let us see, we have a mode shape. Okay, what was my mode shape? V tilde pq sin p pi x by a and sin q pi z by b. Okay. So which means what? My k in the x direction is equal to p pi by a. Okay. So Ka greater than p pi implies k greater than p pi by a implies k greater than kx, the modal wave number. Okay. So these are the modal wave numbers. So now let us see, if the modal wave number is p pi by a, that implies that my modal wavelength is twice pi by kx, which is twice pi by p pi into a, which is equal to twice a by p. Okay. So, lambda x is equal to twice a by p. So, suppose my kx happens to be pi by a, okay, which means p is equal to 1, okay. Then lambda x is equal to twice a, okay. And how does the shape on the panel look like? So, this is my panel length along x direction, okay, and p is 1, which would imply that this is how it looks like. This is p is 1, okay. Why is that? Because lambda x is twice of a. So, if I extend the wavelength into the imaginary distance in x, so this happens to be my lambda x. So, lambda x is twice a. So, which means p or q are the number of half cycles. Okay. So, there is one half cycle on the panel, that is why p is equal to 1. Okay. So, that is how lambda x and a are related, okay. Lambda x and a or lambda z and b are related, okay. So, lambda x is twice a by p and lambda z is twice b by q, okay. So, now getting back to our criterion, the maximum now occurs when k is greater than kx, okay. Similarly, when kb is equal to greater than q pi from here, which implies that k is greater than q pi by b, okay, which implies k is greater than kz, okay. So, again what are we heading towards? We are saying that the k, the acoustic wave number, should be greater than kx, the x panel modal wave number, and k should be greater than kz, which means z direction, kz is z direction panel modal wave number, okay. So, this is indicating the local coincidence, okay. This is not the true full coincidence, this is not the coincidence wave number, but better to see it in terms of lambda. So, what this is saying is that lambda acoustic should be less than lambda x modal wavelength and lambda a should be less than lambda z, the modal wavelength in the z direction, okay. So, that is the maximum condition. So, this is the maximum condition. Okay. We have covered the maximum. What is the condition for maxima? In case a single mode is there in the plate and it is radiating sound. Now, the flip side, what about low frequency. Okay, which means alpha is much less than p pi. Okay, I suddenly mentioned low frequency. Let me just say this, that alpha carries k a sine theta cos phi. Okay, and we said this has to be greater than p pi for good radiation. So k is omega by c. Okay, so greater than means it has to be a certain high frequency. Okay, so we have seen that good radiation is achieved when frequency is high. That is the portion we have just covered. Now we are saying low frequency, that means alpha is much less than p pi and beta is much less than q pi. What happens there? Here in this case it is very simple, because in the intensity, okay, you have many expressions in front and you have this cos sine terms and you have alpha by p pi whole squared minus 1 beta by q pi, etc. So we are examining low values of alpha beta. So these are smaller than, and there is a whole squared also. So these are much smaller than 1. So 1 dominates in the denominator, and I am looking at the maximum value, again the maximum value at low frequencies. Okay. So for the cosines and sines I will take value 1 as the maximum value. Okay. So then what is the intensity? The intensity at low frequencies now is given by twice rho 0 c magnitude V p q whole squared k a b by pi cube r p q whole squared. Okay, this is intensity at low frequency. Okay. Now we will just compare. Okay, at high frequency we will just compare rho 0 c by 2 okay. Now we have to dig into this and understand it a little bit more. Okay. So what we do is, let us look at, so this is the radiation from the entire panel. Okay, intensity, far field intensity, far field time averaged intensity, far field time averaged intensity, okay, at low frequencies. So now we will try to compare it with the intensity radiated, okay, radiated from a single cell from a single cell. That means what? We have this panel or plate is vibrating in some mode, okay, vibrating in some mode. These are the modal half cycle regions, plus, minus, etc. Okay, so we are going to look at radiation from one cell. Okay, so let's see now. Okay, now let me just remind you, low frequency, which means Ka sin theta cos phi is less than p pi, okay, or Ka is less than p pi, okay, which implies K is less than p pi by A, or lambda is greater than lambda x. Lambda, the acoustic wavelength, is greater than lambda x, the panel modal wavelength. Okay. Similarly, lambda is greater than lambda z, the panel modal wavelength in the z direction. Okay. So now if the lambda is bigger, let's say this is lambda, and it's bigger than the entire wavelength in the x and z direction of the panel, which means the single cell dimensions are, both directions are much less than acoustic wavelength. Okay. So we will consider this a monopole. That's what I was driving at. Okay. So now what is the area? What is the area of the single cell? Area is A by P into B by Q. Okay, that's AB by PQ. Okay. And what is the volume velocity? So we are going to compute intensity from a monopole. Okay. So we need volume velocity. When the whole panel is vibrating as V tilde PQ sin B pi x by A and sin Q pi Z by B. Okay. So if I look at one direction, the whole panel is doing something like this. Okay. And somewhere I have a small cell sitting, okay, in the 2D panel, somewhere there is a small cell sitting. So I have to compute the volume velocity from that single cell. Okay. And I will mention this, that we have a radiator placed in a baffle, and therefore the baffle effect is to double the volume velocity. So I will straight away assume this volume velocity gets doubled. Okay, this I am hoping you know from acoustics. Okay. So my volume velocity now, which I will, let's say Q PQ, is given by twice V tilde PQ integral now from 0 to a by p and integral 0 to b by q sine p pi x over a sine q pi z over b dx dz. Okay. If you compute this, we will get v tilde pq 8a by pi square pq, that is the volume velocity. Okay. So let's do this calculation now of computing far field intensity of a monopole, Okay. So if you recall, the green function, okay, was given by e to the power of minus j k r by 4 pi r. Okay. And now to convert the green function to pressure units, I need j omega rho, the volume velocity, e to the power of minus j k r by 4 pi r. Okay. So now in order to convert this pressure to intensity, I need first the magnitude of pressure, which is omega rho q by 4 pi r. Then I need magnitude pressure squared by 2 rho 0 c, which is omega square rho square q square by 16 pi square r square into, so let me make it rho 0, okay, mean fluid density, and twice rho 0 c. Okay. Now q we just found out was v tilde pq into 8ab by pi square pq. Okay. So now if I substitute this q into this expression and do all the cancellations, etc., I will get twice rho 0 c v tilde pq kab by pi square pi cube r pq whole squared. Okay. This is intensity from a single cell. Okay. So let me stop here. The time is running out. We'll start from here next class. Thank you.